We're about to do some physics real quick. Oh my goodness, it's been a while since I have made any sort of math, physics, whatever, video, economics, God have you, whatever educational nerdy thing I'm gonna do today. But y'all, it's been a crazy past year. My friends can vouch for this. I got stuck in Singapore basically for a year because of COVID. And I was only able to finally do a normal semester at University of Texas at Austin this semester. So I'm now a sophomore in college. I'm wrapping up my first semester of sophomore year. I got finals. I just have one left, physics, next Tuesday. And what better way to prepare or to procrastinate than by doing a physics video? So today I'm going to be doing the poster boy example of this entire class. The very first day you step in a class about waves, you gotta talk about the simple harmonic oscillator. Y'all already know. So today I'm gonna be describing, basically we're gonna have an immovable wall. We're going to have a spring and then a mass on a frictionless surface. And we're going to be deriving the equations of motion for it and also solving for its position as a function of time. So this is the very first thing you'll learn in a waves class, probably if your college offers a waves class, and it's definitely something you will consider in AP Physics in high school when you talk about simple harmonic motion or simple harmonic oscillation. So I'm going to be doing everything. We're going to be setting up the differential equation. We're going to be solving it, and yeah, that's what we're going to be doing today. So let me describe what I have for you today. I need to make sure I'm not walking off screen. Okay, so we have an immovable wall and a frictionless surface. And what I'm gonna do is I'm gonna place a spring right here of spring constant lowercase k. That's a K. I still suck at writing on chalkboards, but, and then we're gonna have our point mass of mass M. And then we're gonna say it's oscillating about some equilibrium position down here. I should have done the Walter Lewin trick, this thing. Yeah, y'all know what I'm talking about. I still suck at it though, so I'm not gonna flex it right now. But we have this equilibrium position. I'm gonna call it x equals 0 right here. All right, so we want to find the displacement of this point mass about this equilibrium position with respect to time. So I want this displacement, this x value right here as a function of time. How is it going to change as a function of time? And the first thing which I'm going to do, it's probably the first thing you'll ever learn how to do, like one of the first things besides kinematics, is to draw a free body diagram for this thing right here. So what I'm gonna do is typically you set your positive direction in the direction of the motion, and what I'm gonna say at this instant in time is this point mass is moving to the right, okay? So I'm gonna say this is the positive x direction. Can you even see that? You can, kind of. I'm gonna write a little bit bigger. So first thing, I'm gonna draw a free body diagram for our little mass right here. So we have our point mass, and I'm not going to draw your coordinate axes, but typically you do. So I'm just going to say this is going to be y, this is going to be x. So positive is this way for y, positive is this way for x. So at this point in time, we have disturbed the string, okay? Since the equilibrium position of the mass is over here and it's shifted to the right slightly, you've pulled this spring by a distance x. You've elongated it, okay, by a distance x. And I don't know if you've handled a spring before, but what you're gonna do is when you pull a spring to the right, for example, this way, what's gonna end up happening is the spring's gonna pull back on you. Okay, so what the spring force actually is, the force that the spring exerts on you when you pull it, it's actually what you call restorative, meaning it wants you to pull it back to the length where it was just chilling. All right, it was fine, it was vibing, and then you went ahead and pulled it, so it's like, I want to get back, okay? Same thing, if you compress it, it's gonna push at you. Okay, it's gonna push outward this way. If I compress a spring this way, it's gonna push at me this way. It's like, nah, bro, I don't like what you're doing. I wanna go back to equilibrium, okay? So this is equilibrium, I push it this way, equilibrium is that way, so the spring's gonna push that way. So it's restorative, that's the meaning of restorative, okay? Always wants to go back to equilibrium. So in this case, if I pulled it this way, equilibrium is this way, meaning the spring is gonna be pulling this way. So the spring force is gonna be like so. Whoop! Very cool. And for sake of time, I'm not gonna be labeling gravity. Gravity is a real thing here. It's down, but it's not gonna be, you know, anything contributing to the motion, okay, of this mass right here. So we just have one force in the x direction. So what I'm gonna do is I'm gonna say, all right, the equation that everybody knows, sum of the forces is equal to mass times the acceleration, okay? And I'm gonna say sum of the forces in the x specifically and the acceleration in the x direction specifically. So what is our force? We have our spring force, but I label my positive direction this way to my right, meaning it's gonna get a negative sign out front. So we have the negative spring force is equal to m, and then if you know from the definition of acceleration, this is the second derivative of position with respect to time. So I'm just gonna go ahead and write it out. X double dot. So this dot actually represents a derivative with respect to time. It's a very common notation in physics. Yeah, new notation. Okay, and what is the magnitude of the spring force? It is simply something called the spring constant. It's an intrinsic property of the string, okay, it's a quality of it, times how much you stretched it or compressed it. So we've stretched it by distance x, so we have k times how much you've compressed or stretched it. We've stretched it by distance x, so it's negative kx is equal to mx double dot. Make sure I can see it. Okay, can I? Yeah, basically. Okay, cool. So what now? Well, what I'm gonna do is I'm gonna add this on both sides, flip it around so it looks a little bit, you know, cool. I guess it's a standard way of writing it. So we have mx double dot is equal to kx is equal to 0. And I'm gonna divide both sides by m. I'm gonna say the mass is non-zero, just for those who are nitpicky. So we have a km, k over m times x is equal to 0. Now what we wanna do is we wanna solve for this x right here. And this is a second order, linear, ordinary, homogeneous differential equation. If you've taken a differential equations class, this is going to be, you know, one of the things you've probably studied. This thing is everywhere. But if you haven't, it's okay. I will walk you through the process of doing it. So I will try and give a little bit of motivation for what you're doing here. So essentially, you want to find a function, x, that when you add some multiple of it, okay, k over m is some number like 2 or 0.5 or whatever, it's a multiple of the original function, you get 0. So a couple of functions come into mind. Sine, okay, if you take two derivatives of it, you get negative sine, right? Derivative sine is cosine, take the derivative of cosine, you're gonna get negative sine. Okay, when you add them together, you get 0. Sine plus negative sine equals 0. Cosine works as well, but for reasons that I will probably go into detail in some other video, think about the exponential function, okay? It's great. For example, if I assume that I have x is equal to e to some r times t, okay? Why t? Because x is a function of time, okay? That position is going to change with respect to time. Well, if I take a derivative of this, I'm going to get x dot with respect to time is going to be chain rule, so r e to the rt, and I'm going to take another derivative of it. We're going to get x double dot is equal to chain rule again, r squared e to the rt. Well, Now, if I add these together, what's going to happen? And put them in this, basically this specific equation right here. We're ending up, what you end up going to say is, well, if I add these together and I get 0, okay, and of course there's this multiple out front, well, I want to find out what this r is going to be. So in order to make sure that I have this, x double dot, plus a multiple of x equal to 0, I gotta find out what this is, bro, okay? So if I want to find out any more information so I can set it equal to 0, I need what this r is. So what I'm gonna do is I'm gonna plug this back into here. So I'm gonna have x double dot, so this is r squared, e to the rt plus k over m, and x is just e to the rt. Okay? So now what am I going to do? Well, I can factor this out. So I'm going to have e to the rt is equal to r squared plus k over m is equal to 0. So we have this equation right here. Well, e to the anything is never going to equal 0. So I can safely say, if I have two things that are multiplying each other and they're equal to 0, it means one of them has to be equal to 0, okay? That's not equal to 0, which means this has to be equal to 0. So we have r squared plus k over m is equal to 0. And then we're going to subtract k over m on both sides. Negative k over m. Take the square root of both sides. We're going to get r plus or minus square root negative k over m. If I distribute this square root, this is really negative 1 times k over m. So if you have two things multiplying underneath the square root, you can distribute the square root across both of them. So we have r is equal to plus or minus square root negative 1 times square root k over m. Or this square root of negative 1 is defined to be I, your imaginary unit. So we have plus or minus square root k over m times I. Okay, so what now? If you've taken a differential equations class, this specific value of r corresponds to a very, very specific solution for, well, a specific, no, let's not use specific, a type of general solution for this x. So unfortunately, I'm not a mathematician. I cannot go into the rigor of this, and it would make this video way too long anyway. So yeah, I'm just going to tell you what, given this value of r, mathematicians said that for this specific value of r, it's imaginary. This x is going to take on a specific kind of, I guess, form. Okay, so the general solution for an imaginary root is going to be x is equal to e to the alpha t cosine of beta t plus e, wait, excuse me, I have forgotten something. Okay, x c1, some arbitrary constant, this chunk plus e to the alpha t sine, I also forgot, some arbitrary constant c2, e to the alpha t sine of beta t, where c1 and c2 are arbitrary constants. And this alpha and this beta is going to correspond to, am I walking off of the board here? For our root being alpha plus or minus beta I. So that's what those alpha and betas are. So in this case, our alpha is 0 and our beta is the square root k over m. So I'm gonna go ahead and plug it in here. So x is equal to c1, e to the alpha t, alpha is 0, e to the alpha t, so e to the 0 times t, e to the 0, e to the 0 is just 1. So, bye-bye, I don't have to write that down. And then cosine of beta t. Beta t, beta is square root k over m. That was a terrible K. I'm gonna walk off the board here, aren't I? Okay, I'm gonna write the next part here. Plus C2 sine of square root K over M T. So this is not your standard answer as what you would see in a physics class, but this is the general solution, okay, which describes the position X as a function of time for this specific setup. So what I'm gonna do is I'm gonna erase everything and then I'm gonna transfer this over here. So, chalkboards are kind of fun, but when you have allergies like me, this is gonna be pain. Okay. Spain, but the S is silent. So I'm gonna transfer this over here. Square root K over M T plus C2 sine square root K over M times T. Okay, so this is not the standard form. You're used to seeing this if you're taking a physics class. So here's what I'm gonna propose, okay? I'm gonna say, instead of having a cosine and a sine term, I'm gonna have just one of them. And then I'm gonna have some little thing inside the cosine which makes it true, okay? So I don't know if you guys remember the trigonometric identity for the addition formulas for the cosine. If you kind of remember, you have, for example, cosine A plus B is equal to cosine of A, cosine of B, minus sine of A, sine of B. That kind of looks like this. So what I'm going to propose is I'm going to write X is equal to some constant A, cosine of square root K over M T minus some arbitrary constant phi in here. And you're gonna be like, what the hell, Jose? What? This isn't, where did this come from? You just whipped this out of nowhere? I know, that's how I felt the first time too, but here's what I'm gonna do. I'm gonna expand this cosine out, use trigonometric identities, and then I'm gonna say, okay, if I expand this out and I get it to match this form, what do these constants have to be in order to satisfy it? Or can I even have these two constants to satisfy this thing to make this true? So here's what I'm gonna do. If y'all recall the trigonometric identity for the cosine addition and subtraction formulas, we have cosine of the first thing, square root K over MT. What is that? Okay, cosine of the second thing, this phi, then plus sine of the first thing, square root K over M T, and then sine of the second thing, sine of phi. And if I distribute this A into here, we're gonna get X is equal to A. I'm gonna move this cosine of phi out front. It's okay because when you multiply two things together, the order in which you multiply them is up to you. And then distribute this A into here as well. A, bring the sine phi out front. And what do we have here? So this looks like our top equation, right? So essentially, A is a constant, cosine of phi I told you is a constant, so cosine of phi is a constant. It's just a number. If phi was like pi over 2, there's just cosine of pi over 2, that's just 0. That's a number. It's a constant, basically. So I have a constant right here, a constant right there, and then this cosine of blah, 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 t right here, which is great. And then over here, C2, A is a constant, sine of phi is a constant, phi is just a number, and so two constants multiplying each other, that's just a constant, and the C2 is a constant, which is awesome. So this basically says that this form is okay so long as our C1 is equal to A cosine of phi, and our C2 is equal to A sine of phi. So I have justified that I can write it in this form. So we have our final solution is X is equal to a cosine of square root k over m times t minus some arbitrary constant phi, some phase angle phi. And that's our final answer. And if you're still not satisfied with this square root k over m, let's look at the dimensions of it, okay? So if I look at the dimensions of k over m, this is spring constant and its units are newtons per meter. So we have newtons per meter over m. Sorry, there's two m's in here. This is mass, so its units are kilograms, okay? And what is a Newton? A Newton is a kilogram times meters per second squared. So this is really kilograms times meters per second squared. I'm gonna bring this meters down here. So kilograms times meters, okay? So what do you know? The kilograms times meters cancels out. So we're just left with 1 over second squared, which this is basically 1 over seconds, the whole thing squared. And 1 over seconds, I don't know if you know, but this is actually the units for a frequency. So per second, that's a hertz, okay? Some German out there is probably listening to me pronounce hertz and it hurts for him. Haha. But this is units of frequency. So this is units of frequency squared, excuse me. Okay, so this k over m, I'm just gonna rewrite it as some angular frequency. And typically the Greek letter you use for that is omega. So I'm gonna just say omega squared, because it's angular frequency squared, is equal to k over m. And for those who have taken a physics class, you know that omega has units of radians per second. But the radian is a natural unit, so it's actually implied in here. I know this is a little bit confusing, but if you look at the arc length formula, S is equal to R theta, S is in meters, R is in meters, but theta is in radians. So yeah, radians is a natural unit. So I can rewrite this as basically omega squared is equal to k over m, because the units of this is frequency squared. So omega is equal to square root k over m, and I can substitute that into here for our final form. So x as a function of time is equal to a cosine of omega t minus phi. And this is our solution, dude. Okay, so what do these arbitrary constants actually mean, voice crack? This A actually physically corresponds to the amplitude of oscillation, meaning the farthest this mass can oscillate from this equilibrium position. So say if the mass ends up going all the way over here, but then it starts going back, that's the farthest it can get displaced from equilibrium. And that distance from here, the equilibrium, to where my right hand is at right now, that would be the amplitude. This phi just corresponds to, I don't know if you remember from pre-cal, but this is kind of like a shift, okay, on the x-axis. You know when you have a sine of vt plus c, remember from pre-cal, that c corresponds to you shifting your sine curve back and forth on the x-axis. So this is called a phase shift. Really, if you were to plot this thing just shifts it, you know, right or left, depending if it's positive or negative. Okay, and yeah, so that is it. And does this make sense? Physically, does it make sense? Does it make sense? So what's going to end up happening here is this solution says it's a cosine. So if you remember what a cosine looks like, it's a little wave going up and down, like it's jumping above and below the x-axis. So what this basically says is, as a function of time, this x is going to vary like that. So what's going to happen is this mass is going to go over here, and then after reaching its maximum value, once this cosine reaches 1, x of t is going to be equal to a, the amplitude. And once you hit the amplitude, you're going to go whoop, back this way, and suddenly you're going to stop over here, the amplitude again, and then you're going to go back. And so you're going to have this oscillatory motion going back and forth like this. So this is simple harmonic motion at its most basic, basically setup. And yeah, so this is pretty cool. Essentially, if you have like a mass, say this was like ice or something, yeah, if you just pull it and then let go, woo, just let it go like that, it's just gonna wiggle back and forth, wiggle, 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 okay? So yeah, that is gonna be a nice little basic review for me and for my classmates for watching, I don't know. But yeah, hope you guys enjoyed. I'll see you in the next one. Peace.